Hello everyone, welcome to this KTaNE modding tutorial. Today I will be explaining how to make a puzzle module, since puzzle modules are not the easiest thing to make. So, as you can see, I have not really made any assets. That is because today we'll only be focusing on code. That's also why this console window is so big, because basically the only thing we're going to pay attention to is what our logging is going to say when we are going to make this. So, in advance I have already made some bits of code, like this constraints setup. This is just for myself to make things easier, because I am going to have to make a lot of things that are very similar to each other. Because I will be making a VariantSudoku module for this tutorial. The idea is very simple, it's just a 6x6 Sudoku, but there's variant rules. So there could be rules like sandwich clues on the outside, which indicate how many numbers as a sum are in between 1 and 6. Or it could be something like thermos, which give you a line among which the numbers have to be strictly ascending. Stuff like that. So I have made these this set of constraints. I have made another class that's basically the options that a cell has, because when doing a Sudoku, some cells have some options and you're trying to eliminate options each time until each cell has exactly one option. Other than that, I have this empty class, which will be one of our constraints. So let's give it sudoku constraints. And this is why I made these interfaces, because all of these things are going to behave very similar. Actually, let's just now realizing something. No, we can resolve this a different way. Not reducible. So, let's just get started. So first, what we want to do is probably make sure we have some constraints to work with. In this case, we have some row that this constraint is part of. Sudoku row constraints. This row. I have decided on this module being a 6x6, so I'm not really gonna bother with extending it to be compatible with any size. So what I'll be doing here is, yeah. So this grid is gonna have a bunch of cells with a bunch of options. We're just gonna look at the options in the row that we are in. So sudo cell option array this row is equal to enumerable range 0, 6 select 6 times row plus x. What I'm doing here is just I'm getting the stuff in a row, because I am going to sort my values like if I have 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6, 1. Why not? 4, 5, 6. 1, 2, 3. I'm going to store my rows like this. So I am going to have to step out 6 for every row and then just index everything else in that row, which is what this is basically doing. So now we have a row. Now I can do something. So I will be adding 2 constraints to make sure that, or well, not 2 constraints, 2 ways to reduce a row. Those will be as follows. If there is a number in a specific cell in the row, everything else cannot be that number. And the other constraint that I will be adding is if something has only the possibility of, if only one cell has the possibility of being a value, it will be changed into that value. I will not be accounting for pairs or any other shenanigans. Because that would be too much effort really, and this algorithm won't take too long on a 6x6, I hope. If it does, that might be a consideration for the future. So, let's get started. The first constraint of the 2 is pretty easy. We can just go through each. Actually, yeah, why not? Let's just do it with a for loop. Yeah. Okay. This row length. If this row of I dot entropy is equal to 1, which for context I added that in Sudoku cell options. Entropy is basically how many options it has. I decided on this because that way I can access the cells with the fewest options more easily. However, you can implement this in any way you wish. Let's do this a bit more elegantly. If it's not 1, let's continue. So that's otherwise. Actually, I can remove these brackets. Otherwise, if I is equal to j, continue. If this row of j How did I do this? Options. Its value is equal to this row dot index of no, I'm doing this incorrectly. Inner range index of this row of I options of x. So this will get the index of the value that was in fact the possibility, which will be only one value because of this. So if it actually had that option, we can say that we did reduce it. And we can eliminate that value from being a possibility. Because this is all handled by references, we don't actually need to do anything else, because the Sudoku cell options in here are being thrown in here. Which is quite convenient. Now there's the second constraint. So the other possibility is there's only one position that has a specific value. So let's see how many numbers actually have that possibility. If this is equal to 1, that means that there's exactly one thing that has the option. Actually, if this is not 1, continue. The reason I'm using all this continue is to just make sure that my code doesn't look like symbolic coordinates with all of its indenting. Because we don't want 20 lines of indenting at some points. Alright, so we have an index. We need to look for the element x with options I. Okay. If this row dot entropy, this row of index dot entropy is equal to 1, continue. So if there was already only one option, or well, if that already was the only option for that cell, we don't have to worry about it. Otherwise, did reduce is true. For int j is less than this row length. No. This is just 6. There's 6 possibilities. This row of index dot eliminate j. However, we need to not do that if I is equal to j, which would imply that we're removing the index that, or removing the value that we want that index to be. Now, to make sure that we actually get everything, do all of this while template reduce. Alright. Now, the annoying thing is that we can't really check this without creating a puzzle generator as well. So, at least we have one constraint now. I should probably make sure that it's return did reduce. I'm going to copy this. That was cutting. So now each iteration, whenever it finds something to reduce, it will try again to see if it might be able to reduce something more. That should handle cases where, for example, you have a 1 here with a 1, 2 here and a 2, 3 here. Like the 1 would reduce this. This 2 would then reduce this. So now multiple reductions can be done at the same time. Alright, that's that reduction constraints. You'll notice that the column constraint will be practically the same, except I change one small thing. Which makes me feel like I should probably adjust this. But we'll get there when we get there. Okay. So, I also have this empty class. This empty class is going to be our puzzle class. And this thing is going to be the more difficult class to write. Also, yes, you could all do this in one script, but once again, I am used to object-oriented programming, and this is just slightly more convenient for what we're doing. So, let's see. A puzzle has probably an array that is the grid. Let's make it private. Yeah, let's just make it a list for now. So, Sudoku solution. That's not what I want to use. Using system.collections.generic. There we go. This should not be Sudoku solution. This should be Sudoku base Sudoku constraints. Base constraints. And this should be extra constraints. All right. Now we need a way to generate a puzzle. Public Sudoku puzzle. All right. This is going to be our array of options. I'm doing it like this because if I use enumerable.repeat, there's a risk of duplication. I did not read documentation correctly. Or not properly, whatever. For the base constraints, new list of Sudoku constraints, extra constraints, same thing. Base constraints dot add new Sudoku row constraints for row 0. And let's just do this in a for loop. Now we will get a row constraint for every row. However, it still needs to be checked. So, public void reduce actually no, let's make this return an enumerable of Sudoku puzzles. So this is going to return all the possible reductions that can be made. Or alternatively, I could make it stop at the first point where it needs bifurcation. Yeah, let's just make it stop at the first point where it needs bifurcation. In which case I can just make it return a void. Okay, so list of Sudoku constraints, all constraints is equal to base constraints dot concat extra constraints dot to lists. And let's just make a very simple algorithm that does this. Bool did reduce is equal to false. Although let's make it do while did reduce. And let's make a for each. For each Sudoku constraints, in all constraints, if constraint dots reduce grid. Wait, no. We can do this more efficiently. Did reduce or equals this. This gives us a boolean. And this needs to be at the start of this method. And now all we're doing is basically saying if the constraint has reduced it, we can say that we did reduce it that iteration. So we might want to go again through the earlier constraints to see if there was any interaction between them. Now the difficult part. Public. Enumerable dots. Wait, no. What am I doing? Public enumerable of Sudoku puzzles. Bifurcates. Because we're not always as lucky as we want to be. For this purpose, I'm also going to make a copy constructor. Something that's very similar to what you're actually supposed to do in C++, but I am doing it in C#. No, I don't want puzzle alt underscore grid is equal to grid.select new Sudoku cell option of that type, because I also made a constructor for that. Dots to array. So now each option will be copied into the new grid. We're doing this to make sure that it doesn't copy the references over. Because that's the downside of object-oriented programming. There's a lot of reference stuff, and sometimes you just want the values instead of the references. It can be an advantage, it can also be a disadvantage. Depends on which situation. Score base constraints is equal to new list Sudoku constraints. Actually, we only need to do that with the extra constraints because the base constraints will be static. And base constraints is equal to old dots base constraints. And now that I'm realizing this should be old dots grid. This should be old dots extra constraints. You're also noticing I'm using these underscores for private variables. It's just convenience. You can instantly see when something is a private variable or not. It does look a bit awkward when I'm doing copy constructors like this though. But that's a trade-off. Alright. Now bifurcation. This is where we basically branch off into different cases. So let's see. So we have a puzzle and we have an index. All the bifurcations are going to be list of Sudoku puzzle bifurcations is equal to new list of Sudoku puzzle. Now I is less than 6 because that's how many possibilities we have. If not grid of index dot options of I. So if it doesn't have the option, let's just continue. We don't have to worry too much. Otherwise, yeah, otherwise we are going to use Sudoku puzzle bifurcation is equal to a new Sudoku puzzle Yeah, let's just do it like this. Why not? New Sudoku puzzle. This. So we're copying this. Then we are going to have to adjust the one element that we are trying to bifurcate on. So cell option is equal to bifurcation dot grid of index. No, yes, index. J is less than 6. And this is going to look a lot like this. So I'm just going to steal this code. This is going to be option. And now I just need to eliminate one of these for loops. So now it's just going to eliminate every option except for the option that we're selecting for this bifurcation. And it's going to do that on the bifurcation. Bifurcations dot add bifurcation. Bifurcations is going to be the thing we return. And now we have all possible branches for a certain case, given a certain index. Now let's also make something that checks for entropy, because I'm secretly implementing wave function collapse here, which is basically an algorithm that looks for the cell with the lowest amount of possibilities and branches out from there, because it's most likely to be correct that way. So, let's get started. Okay. So, public enumerable ints weakest indices alright, list of ints weakest indices is equal to new list. For each, wait, no, for I, no, great, that's the Java shortcut. For int I is less than grid dot length int lowest entropy is equal to 7. This could literally be anything. I'm just making it 7 because I know that everything in the grid has to be at most entropy 6. If grid of I dot entropy, hold on, int entropy is equal to this. If entropy is less than lowest entropy is equal to entropy weakest indices is new list of ints with just I in it, because that's the new lowest. Continue. If entropy is equal to lowest entropy, weakest indices dot add entropy. Wait, no. Weakest indices dot add I. What am I doing? Continue. But now, most importantly, if entropy is equal to 1, continue. Because cells that are already determined are not going to be participating. Actually, let's code it safely. Do this. Return weakest indices. Also, this step is completely optional. It's just my preference because wave function collapse is pretty cool. Now we actually need to generate. Public static Sudoku puzzle generates okay. So to generate, what we're gonna do is we're gonna have a stack. Possibilities dot push new Sudoku puzzle. So this puzzle is going to have every single possibility. But now we have these, and these three are supposedly sufficient to reduce this to one possible Sudoku. Of course, I haven't done the column or box constraints yet. However, we should see that every row has only unique values. So, let's get started. Okay, while possibilities.count is greater than 0, return null if we go here. Means that we've run into trouble. Maybe I'll just make a throw an exception. Throw new exception. Could not generate Sudoku. Okay, so all the possibilities are greater than 0. We want to Sudoku puzzle possibility is equal to new Sudoku puzzle. Wait, no, not new Sudoku. What am I doing? Possibilities dot pop. Just getting the last elements. Now I am going to also use Unity Engine here. You'll see why in a bit. Possibility dot reduce. Possibility dot bifurcate. Possibility dot weakest indices dot big random. And now this is INumerable of Sudoku puzzle. New possibilities This should be one thing. Now, for each Sudoku puzzle, new possibility in new possibilities, possibilities dot push new possibility. And now there's one more thing that I need to check. Which is, after it's reduced, there is no problematic value. Public bool is broken. Let's just complete this. And entropy is okay. We can do this more easily. If grid of entropy is equal to 0, return true. Return false. So if any has an entropy of 0, that means that that cell has no possibilities, which means that it's broken. Now similarly, let's make an isSolved method. If it's not equal to 1, then we know that it's false. Otherwise, it must be true. If everything is equal to 1, then it's solved. Because every cell would have only one possibility, which is the solution possibility. Note, not everything works like this, but this puzzle module can actually use this property. Let's see. Now, if possibility dot is broken, continue. If possibility dot is solved, return possibility. And this is basically the algorithm that we'll be using to generate the initial solution. But this part is basically just solving a Sudoku. Except for the part that there's multiple solutions and this thing selects which solution gets priority. Actually let's actually make this not toList dot shuffle to make sure that every possibility gets an equal chance. Because the latest possibility is going to get the most priority. So this is going to be our solving algorithm, supposedly. Let's go to our VariantSudokuScript and get started on some code here. Sudoku puzzle equals new Sudoku puzzle. Except we're not going to use this. We are going to use Sudoku puzzle.generate because that's where we put our code. Now we want to also be able to see what we're doing, so let's log the puzzle. Alt enter, generate overrides. I just need toString, thank you. Okay. So we are going to just return grid dots select x dots right now enumerable dots range 0 through 6. Let's just open it with the square brackets open. Plus this. Join. So that this is going to be a string plus this. I'm just formatting this so that I can easily read what's going on. And here we select x.options of y. And this should be where. And this should function. However, there's only one way to find out. Oh. 0 left please, spaces, yes. I don't like inconsistent line endings. And let's see what we get. We get a bunch of cells with exactly one option. And let's see. Well, we've got a lot of 2's here. So that's pretty troublesome. But remember, we didn't add the column constraints yet. However, I do see in every row that every number appears exactly once. Which, I think I can be pretty content with that. So the most basic part of the puzzle generation algorithm is now there. Let's rename this. This is going to be Sudoku region constraints. This is going to be an int array indices. Right, int array indices underscore indices equals indices. Sudoku row. This is going to be indices.select those items in the grid. And this is going to be called this region. Now, of course, lovely and all, but it's not exactly pretty to keep inserting rules. Because now we need to, for example, new int array 0, 1, 2, 3, 4, 5. We can't just very prettily do it like this. We would have to do 6, 7, 8, 9, 10, etc., etc., etc. So you know what we do? We make a factory for those. Which is also why I added these things. So, let's actually rename this. Public class Sudoku row constraints factory extends Sudoku base constraint factory, which has this one property. So lists of Sudoku region constraints is equal to new list of Sudoku region constraints for int I is less than 6, constraints dot add new Sudoku region constraints enumerable dot range 0, 6 dot select x plus I times 6. Dot to array, because we need an array. And now we return constraints. Well, we don't need them anyway, so let's just do it like that. So, next up. Let's add our column constraints as well. Great thing is, this is all I have to change. Boxes are a bit trickier. We'll get back to those, but for now, let's enjoy a Latin square generation. Oh yeah, I'm an idiot. Sudoku puzzle. Yeah. So, base constraints dot add range. Sudoku row constraints factory. Get constraints. Sudoku column constraint factory dot get constraints. All right. We should now be able to see that both the rows and the columns are completely distinct. So let's observe and see if I am in fact correct on that. Alright, I see no discrepancies there, nothing there, nothing there, nothing there, nothing there, nothing there. I think that's functional. So, let's add in one final region constraint. Which is going to be Sudoku box. I accidentally renamed it incorrectly. I need to rename just this. Alright. So the box is in a 6x6. Or I'll grab paint to visualize that. Box is in a 6x6. If we have our 6x6 like this, they look something like this. They're 3x2 each. So I need can I do this with a clever formula is the question. The answer is yes, I can. The question is how. Okay, so we're going to use x modulo 3. I plus x over 3. And I is actually going to be, okay, plus 3 times I over 2. No, I modulo 2. And this is going to be I divided by 2. But 2 times I divided by 2. And the reason I'm doing this is integer division. So it's going to be either on row 0, 2, or 4. I'm quickly going to do something to check. No, we are not using system.diagnostics, we are using Unity Engine. Debug.log. This.join. Just to make sure that it has the right values. In the meantime, we can add it to our constraints. On to 6, 7, 8, 3, 4, 5, 9, 10, 11, 12, 13, 14, 18, 19, 20. Looks good to me. Find what? Let's not think about that. Let's find what, replace all, find this, replace all. Now if I go in between here, make those. Make those. This should be a valid Sudoku. Well, I see nothing wrong, so I'm gonna assume that it works. And if we do see something wrong, then we'll worry about it then. I'm fairly certain that this works, given all the cases here works, and this is basically just a different type of region. And the coordinates were correct, so I don't see why it shouldn't work. Now, there's one type of constraint that is least appreciated in the variant Sudoku world, but we're gonna have to work with it. It's gonna be the Sudoku value constraints. This constraint will be the most basic of constraints, and you should be able to recognize it when I'm making it. Sudoku constraints. Get reductions. Return new this. The only way to reduce it is by removing it, is what this is saying. Alright, next up. To try and reduce something in the grid. Okay, we're gonna need a constructor. Public Sudoku value constraints. Int index. Private int index. And now let's see. So this thing is going to keep track of the index it's assigned. As well as the value it's assigned. I love auto-completion. And now, to reduce, we just look at one index, and I'm actually going to steal some code. Yeah. I'm gonna steal this. I'm going to steal this because this is basically the same thing. This is going to be grid instead. This is going to be underscore index. And I doesn't exist, that's going to be value. This is going to be I, this is going to be I, this is going to be I. And actually let's swap this. If I is equal to value, continue. Otherwise, eliminate I. And this is how you reduce for a single cell. This is basically just, hey, there's a digit in this cell. Which means that's, yeah, not much to do there. If this is already not an option, we can casually continue. Otherwise, we eliminate and we keep track of a boolean, just like our other constraints. Bolded reduces false. Did reduce is true. Return did reduce. And I'd like to make this or equals. It just feels fancier. It doesn't really change anything. Basically what this is saying is if this is true, it doesn't have to do this operation. Although if it is, then this is still, nah, it doesn't really matter much. Anyhow. We now have our first type of constraints. Let's add a toString. Return row plus index divided by 6 plus 1 plus C plus index modulo 6 plus 1 equals plus and then value plus 1. So this is just going to give me a more clear overview of which constraints are active at a time. Alright, next up. Now that we actually have something to constrain the puzzle by, we can start actually making a solvable puzzle instead of a solved puzzle. So what we're gonna do is we're gonna use our original puzzle and we are going to check if it's unique. And what we're gonna have to do is fidelity counts. This is equal to 0 initially. If possibility is solved, we can't really think of any bifurcations. So what we do is possibility counts plus plus. Continue. If possibility counts. Actually, let's make this a boolean. Bool has possibility. It's false. Has possibility is equal to true. However, if has possibility before that, return false, because that means that this is a second solution. Let's rename this as solution. Return has solution. So if there's no solutions, which is technically impossible, but like edge case, we have this thing. It will return false if there's no solutions. And so this will branch through every single path to check whether or not there is a second solution. Now that we have an isUnique boolean, we can make use of it. And actually I'm thinking I should probably make this a new object. Sudoku puzzle test is equal to new Sudoku puzzle. So it uses that constructor. And we just give it some base constraints, we give it some extra constraints. Let's capitalize this T. Base constraints is equal to base constraints, extra constraints, extra constraints. Now we're pushing this. What this will do is make a new puzzle where still every cell has every possibility, but we have these extra rules in place. Mainly these rules are of importance here. But of course these rules are also necessary, so better off adding them. Alright. Now, we need to make sure that there's all the clues added. Public void generates constraints now I forgot something. Remember this? Why is system.reflection here? I don't need system.reflection. Public class Sudoku value constraints factory extends Sudoku constraints factory. Alright, now we go to Sudoku region constraint because I'm gonna steal some code again. Except this is going to be a slight bit different because I actually need to go through every single element in the grid. New Sudoku constraints thing. Sudoku value constraints. I grid of I. This parameter is a solved grid, so this should in fact work. VariantSudokuScript.cs. Okay. So now that we have this thing, which goes through every single element and adds the value of that element as a property, we can go back here. Array grid is equal to underscore grid dot select x dot options dot index of first true dot to array. Since there's supposed to be only one true value, there should not be an issue with that, except for the fact that I need to use y here. Because of the conflicting x. I'm probably going through this very quickly, but just bear with me. So we have to generate some constraints now. Extra constraints dots add range. New Sudoku value constraint factory. Get constraints for our interarray grid here. So we now have a bunch of extra constraints that will also be checked. Possibility dots generate constraints. If possibility dots is unique, debug.log yay. Just a quick test to see if the isUnique function actually works. Yay or nay. Let's do yay or nay like this. Hopefully we'll be getting a yay. And we are getting a yay. So this is pretty good. Let's just load up a bunch of these. 15 or so. All of them should give back yay. Okay, perfect. So at least the positive side of things is functional. Now let's shuffle lists, just because. If the possibility were to be not unique, then we might want to continue. Basically, if we figure out that whatever we're doing doesn't work out very well, just try a different solution. Maybe that solution is in fact unique. This is something I encountered with piece positioning, for example. You could make it as minimal as possible and give it as many constraints as you're familiar with, but it didn't always succeed. Sometimes it even generated something that could be done within less tiles than given, which is impressive, but a bit unfortunate. So, next up is getting rid of all the constraints that we can get rid of. So let's make a queue. Queue of Sudoku constraints is equal to new queue Sudoku constraint based from possibility dot base constraints. No, extra constraints. Constraints themselves aren't copied, so that's pretty good. Alright. Now, while constraints dot count is greater than 0, we're going to try to remove a constraint. Okay, so current constraints is equal to constraints dot dequeue. So we're getting it out of the queue and into the currently managed thing. Sudoku the constraint no. New puzzle is equal to New Sudoku puzzle possibility. New puzzle, extra constraints, let's remove the current constraints. If new puzzle dots is unique, or rather if it's not unique, we're gonna continue. Otherwise it's gonna be here, and we can say that possibility dots extra constraints dot remove current constraints. Return extra constraints join with commas. So now, instead of being given the puzzle, we are going to be receiving just the clues that we need to resolve the puzzle. And apparently this is plenty. So let's just see if this works. I could have done this more efficiently. Alright, so row 2, column 3 is a 6. Row 5, column 2 is a 6. Row 2, column 6 is a 2. Row 2, column 5 is a 1. Row 5, column 6 is a 1. Row 6, column 5 is a 4. Row 6, column 4 is a 3. Row 1, column 2 is 5. Row 1, column 5 is a 3. Row 4, column 1 is a 5. Row 6, column 2 is a 2, and row 5, column 3 is a 3. Apparently this is solvable. So let's just copy it for safety. So this is a 5. There is a 6 here. Oh, that's not a 6. That's a 6. This is a 1. This is a 4. This is 2. This is a 3. This is a 1. This is a 4. We could also trust the algorithm, but like it's safer to just check. Because the lack of clues in the middle 2 rows is a bit concerning. But who knows, maybe it works out. Well, this is a 6. This is a 6. So this is a 6. Oh, there's a 5 here, there's a 4 here. So there's a 5 here, there's a 2 here. Which means that there's a 2 here. Which brings a 2 here. 1, 2, 3, 4, 5, 6. This needs to be a 4. Which means that the 4 here needs to be here. Which, this needs to be a 1. Which leads to a 1 there. 3 here. 3 there. This is a 5. And as you can see, it's a solvable Sudoku. And apparently in any other situation, it was able to find a different solution that also fits every single constraint. Anyway, that's puzzle generation basically. So for the rest of it, I kind of wanted to add some extra variants. So let's add a new item. And this is why I used object-oriented programming as well, because I can just reuse a lot of code for a lot of things. And I'm using the factory so that I can decide which constraints I will choose for a certain puzzle whenever I get to implement that. Which I am planning on implementing. Yeah, let's start with even odd Sudoku. I don't need all this junk. Let's copy this thing. Just because I'm lazy. Sudoku parity constraint line. Sudoku parity constraints. Yeah, let's just do it with booleans. Constraints. New list of okay, yes. Yeah, okay. Now for the actual parts. Sudoku constraints. Okay. I will be adjusting this sometime. Because I've just been realizing something. Which is, this get reductionist method is currently absolutely useless. The reduce method is not though. Actually, let's do the private fields first. Oh, hold on. I can just do it like this. What am I thinking? I'm adding 1 because 1 is not supposed to be even, but it's registered as 0. So if the parity matches with what it considers even, or whether it considers itself even, hold on. Yeah. If the value is considered of its parity, it doesn't have to worry. Otherwise, it will eliminate the option. And now I can do this. I'm gonna steal this too. And now we've made an even-odd Sudoku. At least not yet. We still need to go here and go to generate constraints. And now we have some parity constraints in the mix. Small priority thing. We now have a new type of Sudoku. Let's see if it actually works. Row 3, column 6 is 6. Row 1, column 6 is a 4. Row 4, column 1 is a 4. Row 1, column 3. No, row 1, column 4 is a 3. Row 2, column 3 is a 1. Row 5, column 6 is even. Row 6, column 1 is odd. Row 3, column 5 is odd. Row 6, column 2 is odd. Row 5, column 1 is odd. So let's see, how much can we achieve here? Well, I know as much as this is even, this is even, this is even, this is odd, this is odd. This is 2, because it sees the other two even numbers in the column. What else can I do? Well, this is 2 then, because these two can't be 2s because of the 2 in a row. Okay, what else can I do? Well, this 4 needs to be in this box, so it's gonna get here, which forces it down here. Which is not exactly helpful. There's a 4 here. So this is a 4, this is a 6. Six can't go here, so the 6 has to go here. Which means that there's a 6 in one of these two spaces. But more importantly, this is an odd number. Additionally, this is an odd number. This is an odd number. And this is just a naked single, this is a 5. So this is a 3. There's a 2 in one of these spaces, so this is odd. Looks like this space is odd, and this space is odd. At this point I'm just confirming to make sure that everything works as intended. Oh, the 3 in this box is forced. So this is not 3, that's not 3, this is 3. Three is cornered into one of these two spaces. 3 here is cornered into that space, so this is another 3. I think that's our 3s. Yeah, it should be. Yep. I also have all my 4s. Do I have all my 2s? I do not have all my 2s yet. Do I have all my 6s? Well, the remaining 6s here are here. Which in fact it's here. So this 6 needs to be here. So this is a 2, which means that this is a 2. And this is a 2, which means that this is a 2. And at this point I just need to make sure that the 1 is properly assigned. Okay. This is a 1, 1, 2, 3, 4, and this is a 5. Which means this is a 1, and this is a 5. Which means this is a 1, and this is a 5. Which means this is a 1, and this is a 5. And this is a 1, and this is a 5. And that looks like a solved Sudoku to me. So, as far as I'm concerned, this looks like it works. Anyway, so how we generated this puzzle was basically we added every single possible constraint, made it as difficult as possible for the puzzle to be solvable, and then step by step we decided to get rid of something to make the puzzle solvable. Step by step we got rid of something to make the puzzle still uniquely solvable, but less given away, basically. Anything that you are able to calculate, it will let you calculate. Now I want to add, yeah, maybe I'll add 2 more. Add new item. What would be most fun to add? How about yeah, let's do Kropki. So basically, Kropki has 2 types of properties. There are black dots, which is if you have numbers connected by black dots, there has to be a ratio of 2 between them. So 1 to 2, 2 to 4, 3 to 6. Those are basically your only options for a black Kropki dot in a 6x6 Sudoku. For white Kropki dots, the numbers have to be consecutive. So you have 1, 2, 2, 3, 3, 4, 4, 5, or 5, 6. And those are the Kropki dot constraints. So, how are we going to do this? Well, let's start off by stealing this thing again. Why did this thing come back? We don't need reflection. Sudoku Kropki constraint factory. This is going to be a bit more difficult. If I modulo 6 is greater than 5, or I divided by 6 is greater than or equal to 5, continue. Okay, now for the horizontal check. Public static int Kropki relation. Wait, no. Let's do this. Int A, int B. And white Kropki relation A and B. Return A minus B equals 1 or B minus A equals 1. White is a difference of 1, either direction. This is return A times 2 equals B, or B times 2 equals A. One of them multiplied by 2 has to be equal to the other. The 1 to 2 ratio. Alright, now private spool is vertical, private spool is black, private index. That's, I believe, it. So public sudoku Kropki constraints. All right. So oh. All right. This again. Reduce is going to be an interesting one. Okay, so my black is equal to sudoku Kropki constraints dots as black Kropki relation grid of I grid of I plus 1. Whites same there. The thing with Kropki is you can't have a black and a white dot in the same position. So if may black and may white is vertical is j is equal to 1, is black is equal to if may black or may white. Actually, no. This is supposed to be an AND. If neither is possible, just continue. Not worth the time. Choice for black is may black. However, if this choice black is equal to this instead. Yeah, no, let's just keep it as was. Black dots are more constraining, so I decided to just pick black as being true. Int alternate index is equal to index plus is vertical. If it's vertical, we add 6, otherwise we add 1. Okay. Now, the tricky part. Actually checking constraints. Okay, so I need to keep track of all the possibilities on one end and all the possibilities on the other. Sudoku cell option. Option 1 is equal to grid of index Sudoku cell option. Option 2 grid of alt index full bit reduce is equal to false. Okay. I is less than 6. If no option 1 no if option 1 dot options of I is not true, continue. We only need to check for the things that are true. If enumerable dot range yeah, we're still good. 0, 6 dot any option 2 build options of x and has black Kropki relation of between I and x. But this needs to be in parentheses because is black has black relation. Otherwise, it's a white Kropki relation. So if any works, continue. Option 1 dot eliminate I. Did reduce is true. Bool needs swap is equal to true. While needs swap let's be fancy here. Needs swap is equal to first time. First time equals false. There we go. If needs swap break. I can make this a while true. If I make this a continue. So if it needs to swap, it will jump back. Otherwise, it will end up here, breakouts. Which, in which case, it needs to return did reduce. If it needs to swap, swap is equal to option 1. Option 1 equals option 2. Option 2 equals swap. And then it swaps them around, checks again, keeps going until it finds nothing. Or at least that's the hope I have. So it returns that thing. Yeah, looks like we have Kropki now. I am going to steal this again. Actually, this entire thing. Coordinate is equal to, if it's vertical, it's going to be r plus x over 6 plus 1 and x over 6 plus 2 plus this. And now I'm just making it fancy and everything. Let's cut this out, paste it here. Make this a modulo. Now I have an if else for all of my needs. Turn coordinates black Kropki dots, white Kropki dots on the is black boolean. And now if we go to a Sudoku puzzle, new Sudoku Kropki constraints factory, and comment out the parity. We get a Kropki Sudoku. So let's see, what do we have here? I managed to make a Sudoku with just the Kropki dots. So let's see what we get. For this, I'm gonna have to broaden this, make it a bit wider. Actually, I don't need these to be wider. I need some spaces here, spaces there, spaces there. Between rows 1 and 2 on column 3 is a white dot. Between rows 3 and 4 on column 5 is a black dot. Between rows... Okay. In row 3, between columns 3 and 4 is a black dot. Rows 2 and 3 in column 1 is a white dot. Row 2, columns 1, 2 is a black dot. Row 4 and 5, wait no, row 4, column 5, 6 is a white dot. Row 1, 2, column 4 is a white dot. Row 4 and 5, column 4 is a white dot. Row 4, 5, column 1 is a white dot. Row 5, columns 1, 2 is a black dot. Just for my own sake, I'm gonna complete these a little bit. Oh my. This is already not easy. So, remember black is 1, 2, 2, 4, 3, 6. I'm not good at those. Neither of these is a 5. These are different parity, these are different parity. If this is a 3, this would be a 6. Can I do something with that? Doesn't look like it's... Yeah, and at this point the issue becomes I have no idea whether or not this is solvable or not. So I'm gonna cheat. Okay, that's unfortunate. Okay, it doesn't seem like I can easily find a solver for this, so that's on one hand convenience, because that means that people can't really cheat this. On the other hand, not so convenience. Okay, that cannot be a 1 because this would be a 2 and this would be a 2. This could be a 2 with this being a 1, and this being a 3, this being a 1. If this is a 2, this needs to be a 4, this needs to be either a 3 or a 5. Oh, this is difficult. I'm just going to assume that it's solvable. Because the module could only find one solution, so there probably is just one solution. And I know that's a very risky thing to say, but feel free to figure out what the solution is for this one. While I quickly decide to log possibility.grid select enumerable range 0 to 6 dots where x no, y x dot options y join close square bracket close of course dot join. And let's generate another one. Yeah, fair enough. And I mean, it generates a solution here. Oh. I see. I see why I couldn't find a solution. It's because this. Now, for the Kropki constraints, I need to check whether or not this matches with this. Yeah. Now we should get a solvable puzzle. Alright, let's see. Row 5, column 6. Oh, it couldn't get rid of all the numbers. Interesting. Row 5, column 6 is a 6. Row 3, column 5 is a 3. Row 2, column 4 is a 3. Row 4, columns 3, 4 is black. Row 1, columns 1, 2 is white. Rows 2 and 3 on column 4 is white. Rows 2 and 3 on column 5 is white. Rows 3 and 4 on column 2 is black. Rows 5 and 6 on column 1 is black. Row 4 and 5 on column 4 is white. Row 5, columns 4, 5 is white. Rows 2 and 3 on column 1 is white. It's still an intimidating puzzle. Okay, so this could be a 6, but at least can't be a 3. This is 6, this is a 3. This would have to have a 2 on it. If this is a 4, and this is a 2, and this is a 2, so this would have to be 6 and 3. How do I solve this? Well, regardless of how I solve that, let's just confirm that this is in fact a valid solution. 2 against 3 is consecutive, 4 against 5 is consecutive, 2 against 4 is that, 3 against 6 is that, 3 against 6 is there. Nice. 3, 4, 3, 2. As you can see, these things get incredibly difficult. Well, that's that constraint. Now time to actually fix something. Because there's this one thing that I've been holding off on fixing, which I need to do for all my constraints actually. These all need to have an empty list. What this means that to reduce it, rather than just write out removing it, we can now enable it to look at the possibilities. And the possibilities of reduction will now be given by the thing itself. So let's go to this. Okay, so we have a collection of Sudoku constraints, but that's also a collection of Sudoku constraints. Alternatives is equal to current constraints dot get reductions. Enumerable of constraints, constraints. So if a constraint cannot be reduced, as in it's not allowed to be removed, that's just the equivalent of saying there are no elements in the alternatives. Saying that it can be removed is giving one empty list. This is just a design choice. Not really anything to stick to. So instead of doing this, I need to then add range the alternatives. Alternative. There we go. If the alternative still leaves the puzzle to be unique, then we're good. If it doesn't, then we aren't. And of course, constraints dot is equal to constraints dot concat alternative dot shuffle. Wait, no, that's to list shuffle. So now it adds in the extra constraints that it found. And shuffles the list afterwards. By this point it should have removed all the numbers that it can remove, so we shouldn't have to worry about that. However, I am going to something for future consideration. What is it saying? Ah, yeah. Well, that's not an actual code error, it's Visual Studio acting up. So what we do is we close Visual Studio, we save this, we go back to Visual Studio, we go to variants. Alright. And it's complaining here because we need to put this in a new queue. And of course I can't type it anonymously, so this is sudoku constraints. And now this should be able to still give us a similar type of result. Looks like it, but I do have to remember that let's order by access sudoku value constraints. I think booleans are sorted like this. If they aren't, we're only gonna see one Kropki clue. Or none. Yeah, of course. We want value constraints to be at the front. Hey, look at that. We get a Kropki only. Interesting. We didn't have that last time. Let's see. I know this takes time, but it's definitely fun to see whether or not this functions. Row 3, columns 2, 3, it's white. Row 1 and 2, column 4, it's white. Row 2 and 3, column 3. It's white. Row 2, columns 1 and 2. White. Row 3 and 4, column 5. It's white. Row 4, columns 4, 5, it's white. Rows 2, 3, column 1, white. Row 5, column 3, 4, row 5, column 3, 4, black. Row 1, column 5, 6 is white. Rows 1 and 2, column 2 is white. Row 4, column 1, 2 is white. So apparently this is resolved. So let's just see. I know about white dots that on one end and on the other end the parity is different. So I can say that this is parity A, this is parity B, this is parity A, this is parity B. Then it becomes tricky. The ABA in this section could just be 1, 2, and 3, could be 4, 5, and 6, could be anything in between. This value can be equal to this value could be equal to this value. So Kropki is very unconstraining. But on the other hand, it's also pretty decently constraining actually. Oh. No. 5 can't be on a black dot, but you can't really do much with that information either. Yeah, I can't solve it like this. I'm not able to solve it, but the module is. So, there is a solution. Two, 3, 4, 3. As I said, these could be equal. These could be equal. This is a 2-4 pair. Makes sense that they share parity. Because if it were a 1-2, would be difficult to spot. Although, I see one way to think about it is these have different parity, these have different parity because these have different parities. Hold on, I might be able to resolve this. So these have different parities and these must have different parities, which means this is C, D, C, D, C in terms of parity. These two have shared parity, these two have shared or different parity, these two have different parity, so this and this must have different parity, so this is an A. So this must be a B. Some really clever parity tricks. Can I solve it with this knowledge though? Whatever. I'm spending so much time on this. Now let's actually add a constraint that helps us out a little bit. Well, every constraint helps us out, never mind. Let's add a constraint that makes use of those reductions. So, there is some number of constraints that make use of them. Let's just do a simple one. Sudoku quadruples constraints. So, the idea with quadruples is as follows. You have 4 spaces that are used each time, and then there's a circle in the middle of those 4 with some number of numbers in them. And basically the numbers in that circle dictate which numbers have to appear in the surrounding 4 cells. So, of course, we will be stealing some code from here again. So this is going to be quadruples. Actually, we just have to... We don't need this. Okay, so quadruple needs an index. And an array of values. Sudoku quadruples constraints. Now, this is part of Sudoku constraints. And yeah, this is really... I'm no longer really working on the puzzle generation. This is just adding more constraints. And as you can see, the puzzle generation just adapts. So I'll be adding this one, and then maybe I'll go a little bit over what exactly we've done. Alright. Quadruplets equals shifts, let's select index plus x, where x is the variable involved. And we want grid of this. We now have an array of 4 elements, which is going to contain the quadruplets we are concerned about. Okay, I want distinct elements. Order by value. And parse it to an array. If there's duplicates, they should be eliminated. Okay. Now. The funny thing is, this is going to be very similar to region constraints second part. So I'm gonna grab this. And this is gonna complain. Then I'm gonna go here. And do this. Okay, can't replace that. Probably because it's undefined. Okay, so if the entropy is 1, we don't care. So any value that doesn't work. If not values that contains I continue needs to just be looking for those values. And of course I could just make it iterate through values, which would probably be the better way of doing this. Yeah, let's make it go through. Value is equal to values of I. Alright, so it checks whether or not. This should work. Now for the reductions, there is this very interesting thing going on. for each value, we can make a new array that emits exactly that value. Except x. So that will exclude the value x from being in there for every x. This is equal to x. New lists of Sudoku constraints. Actually, new Sudoku constraints array, why not? Doesn't really change anything. New Sudoku quadruples constraints. Index values. Equals to array. Enumerable of Sudoku constraints as a cast, because it needs enumerable Sudoku constraint and its contents. Fun. Line 39, 175. Oops, one semicolon to, or one parenthesis close too many. Let's just see. Oh right, I forgot to add the constraints. Or logging for the constraints. Alright. Also with the Kropki constraints, I think I'm gonna get rid of those columns. If you see a double-digit number, you already know what it's talking about, right? No, that's an accident. Now, Now, what's complaining? There's no semicolon there. Alright. Let's see if quadruples work. And if that functions, then the reducing thing should also work. Which, oh my. That's a lot. Let's add parity into the mix as well. And I have to values select one more. Let me verify something. Yes, okay. So what just happened was Unity is struggling with the calculations. Which makes sense because I did not give it the most convenient calculations. So, yeah, it was stuck for a few seconds. Which is an issue that we can resolve with threading. Which, good that this actually happened, because that is in fact a topic might be useful to discuss. Also, how come none of the quad clues have been reduced? Hold on, let me check something. If I do this, debug, log, please tell me it at least works. don't need this section. Okay, let's see. Okay, it does look like it works. It's just apparently the module finds it most convenient to generate with all four every single time. Yeah, the amount of time it needs is not good. That is of course because of the number of active constraints, which yeah, with both quadruples and even odd, both covering practically the entire grid, that is to be anticipated. So yeah, I could quickly add in multi-threading, or just doing this on a separate thread, which would probably be a good idea. So let's get that to work. VariantSudokuScript. All right. Private thread private static pool is using threads. i.e. numerator generates puzzle private sudoku puzzle yield return new wait for seconds. What I'd like to do here is wait for some amount of time, so that's they're just scrambled bits and everything's got time to wait for each other. I don't know, it's just something that I started when I first did threads because it was suggested to me. Or I kind of used a reference. Anyway. Yields, return, new wait while. Is using threads. Is using threads is true. Thread is equal to new thread. And then we just do this. What I'm doing here is anonymous lambda, so, or, yeah, I mean just lambda. So I can just put some code in here that will be run by the thread. Which then gets run when I use thread.start. Puzzle is sudoku.generates. Wait while the puzzle is null. Well, this thing puts is using threads to false after the puzzle has been generated. Actually, for safety, I'll just put that here. I don't know if stuff might switch around if I do it otherwise. Now we can do start coroutine generate puzzle. I'm doing it like this because normally everything is running on the main thread. However, puzzle generation, you don't want that to hold up the entire game. So if you just run it on a thread in the background, you might be better off. Of course, there's also other ways to solve this issue, but this is a simple way to... Oh yeah, right. I forgot about that one. That's one downside of using threads. Yeah. You're stuck without a random function. Or at least you're stuck without Unity's random function. Which is really unfortunate because it's a really convenient random function. So what I'm gonna do is I'm gonna go to one of my other mods real quick, the source code. No. And I'm just gonna steal some functions because I do not want to rewrite them. And this is from, I'm gonna steal some code from raster prime because, yeah. Alright. Now we should get some complaints. However, now I just need to import a random. I'll fix debug.log in a bit. And now basically what I have to do is grab this shuffle and do this. Let me just check. Yeah, it looks like it understands what I want to do. I don't need the shuffle here, do I? Or possibility, but there. Now it's complaining several times. What is it mostly complaining about? Yeah. type arguments for, oh, I'm an idiot. This I don't need that shuffle. What am I doing? This should work. Now all I need to do is now I can go back to using Unity engine. I would think, except there's one more thing. Cannot convert from system.random to system.random. What? Okay. Now there's one more thing that I need to do, which is Kropki needs to have random in there. However, I don't care at the moment. Oh, I forgot to. Might not be too entertaining, but you know what, let's just do the entire range. Oh no, I have to do the other one as well. Alright. So we have shuffle. We also have pick random. Oh. Now for the other one. That should resolve everything for now. If values.length is equal to 1, then it should be able to return this though. Alright. I got rid of the locking line as well, so we should now just get the grid. And after a bit, we should get a solution. Oh look, we've got a quadruplet clue with just 3 elements. Oh, we have multiple. Alright, the one final thing that I'm gonna do is I'm gonna add these back, but this is gonna need random. Because, funny. Because of this here, and now we have a variant Sudoku with 3 different types of rules. So let's see how well it works. Row 1, columns 1 and 2. row 3, 4, column 2, row 4, 5, column 2, this is white. Row 4, 5, column 3 is black. Row 3, 4, column 3 is white. Row 5, 6, column 3 is white. Row 6, column 1. No. Quickly doing all the Kropki dots first. Row 1, 2, column 2 is black. Row 5, columns 1 and 2 is white. Row 4, columns 5 and 6 is white. Now that we know those, let's go on to our even odds, because they're also pretty easy to write down. Row 5, column 1 is even. Row 3, 4, column 2. No. I have an even. I have row 5, column 3 is even. Which means that this is odd. This is odd. This is even. Row 2, column 3 is odd. Actually, I know that this is a 2 because it needs to be a 1, 2, 4. Row 2, column 2 is odd. So this is the 1, this is the 4. Row 2, column 1 is odd. So this is 6. Row and column 2 is even. Yeah, I knew that. Okay, that's something interesting to investigate. Row 5, 6, column 3 is, okay, no, row 6, column 1. This is odd, so this is even. Odd, even, odd, even, odd, even. Okay, so this has to be also, this is a 3, this is a 6. Which means this is a 5. Which means this can be a 6 because this would have to be 3. Which means this is a 4, which means that this is a 2. And this is a 1. This is a 3. This is a 1. This is a 6. This is a 2. Something's telling me that some of these constraints are unnecessary. Well, I trust that it's solvable. But maybe I have to narrow down the possibilities, or at least the choices that it makes. Oh well. Anyway. In conclusion, so I implemented this, in this video I implemented this algorithm which basically, first of all, it just solves a puzzle and picks one random solution. And then from there on it decides to add every single possible constraint, checks if that's unique, and then step by step tries to remove constraints. If it's able to remove them, then it will in fact remove them. Oh. Was that the issue? Seems like it generated a lot less clues. Could be a one-off though. Yeah, looks like it's a one-off. I'll have to investigate this further. I know what's going on. Okay, I'm gonna fix this one thing. That's it, isn't it? Okay, yeah, quadruples are pretty powerful, so fair enough that there's only one now. Also, one advantage of this multi-threading is this doesn't hold up your game. They'll just enter their things one by one. Alright. Oh well, anyway. So, I've shown today how to make a quote-unquote simple puzzle generation algorithm. It's a very general principle that I use for a lot of puzzles, which is simply generates solved states generates all the constraints, gradually remove the constraints that can be removed. And that's basically it. For generating a solved state, your best bet would probably be to do some random depth first search. So basically what I did here was it just looks for something, just eliminates what it can eliminate, then it finds something that has some amount of possibilities, picks a random possibility for that, and then keeps going. And whenever it finds something, it's successful, so yeah, I would call this depth first search, but randomized. Oh yeah, this one is also pretty important. Make sure that whenever you've generated all your constraints, it is in fact a uniquely solvable puzzle. Because if it's not, if not, yeah, if it doesn't succeed, you're gonna have to jump back here, generate a new solved state, generate all of those constraints, make sure that's unique. Oh well. And yeah. and then just whenever you need to remove the constraints that can be removed, start. Yeah, I guess this is easiest explained as you start some kind of trial. If still unique, apply to current puzzle. If not, discard. So yeah, I handled this with that queue, which is right here, constraints. Because in my case, I know if I remove a constraint, I don't have to check again whether or not I can remove that constraint. If I don't remove that constraint, I don't have to worry either. Because if a constraint can't be removed, there is no chance that it will be able to be removed later. That's just how this type of puzzle generation works, I suppose. So yeah. The funny thing is that this already generates a puzzle. Actually, this. This is just to make sure that the puzzle is a bit more interesting. Like, instead of just giving only the things that you need, or every single possible clue on the board, this part makes it so that it's challenging. So if you want more or less challenge, your tweaking would happen here. And it would probably rely on how many things you remove, in what order you remove them, that kind of stuff. What I did here, for example, is make sure that I remove numbers that I can remove first. Anyway, I think that's about it. I don't really have anything more to explain. I've implemented several constraints, which I could implement more, and I will probably implement more, definitely before I release this. But yeah, this should give you some idea on how to generate puzzles. If anything was unclear, I am able to understand that because I've used object-oriented programming, and not many modules use object-oriented programming. This one does because for puzzles it's just way more convenient to do. With object-oriented programming, just think of it as every noun you can think of, you can turn into an object with some properties. So for example, this puzzle, it's a thing. So we can make it into a thing. And this thing has certain things you can do with it. Yeah. I can't really explain it very well. Anyway, I will be putting this source code online. So you'll be able to reference it. And I think that's all for now. Thanks for watching. I hope this helps. And until another time, I guess.